Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. This is lecture 100, Gauss's Law. So we're going to be talking first about flux, which is why I put a picture of, what is that?
A fidget spinner.
A fidget spinner? What is a fidget spinner?
Those little things you spin.
No.
What is it?
What do you think it is, Gabriel?
Oh, I don't know. It could not. It definitely isn't a flux capacitor.
A flux capacitor? Yes, it's a flux capacitor.
That's right. Fidget spinner.
Fidget spinner. That's a new one for me. So, flux, as in the flux capacitor. What is flux, right? So we can think of it, there's several ways. We can think of it as, air currents, right? And we're trying to measure how much air current flows through a surface, okay? Or you can think of it as water flowing through a surface. Maybe a convenient way to think of it would be, we'll take the kind of the reverse image of it. So if I had a big, large piece of wood and I cut a rectangle in the center of it somewhere and I held it up with a light source shining behind it, right? Let's assume it's a uniform light source, like a big flashlight or something like that. The light's going to come through the hole that I've cut, right? And we can think of that as a flux, all right? So we'll, of course, be using it for electric fields. So imagine that we have, an infinite sheet of charge generated a nice uniform electric field, right? And I put some surface out here. Well, for starters, what if I took a surface that was like in the plane, such that if I drew it, right, I drew a normal vector to that surface and compared it to the electric field that we're getting, and this was making a 90-degree angle, right? So it's kind of holding it edge on, right? How much is going to get through the hole, or how much is going to pass through the surface if I hold it flat with respect to the surface? Any ideas? How are we going to get more through, right? Let me use an actual surface, right? If I try to see how much light hits this surface, do I get more through if I turn it sideways like this?
No.
The light's coming in, right? It's completely missing it, right? We get zero through, right? So the flux would be zero in this configuration, yes? Whereas in this configuration, seams would be maximized, right?
Yes.
Yes?
Yes.
So the light. So I get zero if I do it that way. I would get a maximum amount, right, if I place my surface such that the normal vector from the surface was aligned with the electric field, right? Yes?
Yes.
And so we're going to define it as, call it a little del phi, would in this case be equal to E times, I'll call it del A, where the area of this is del A, okay? Obviously, I want to shrink that down, yes? That's why I'm calling it delta A, right?
Yeah.
I said del A, I meant delta A. So a little piece of area, right? So I'm defining the flux as the field. And this, of course, would be the magnitude of the field times this del A, delta A. Why do I keep wanting to say del A? There is a del operator, by the way. So maybe that's why. So what if I turn it at an arbitrary angle, right? Let's see if I can draw that. It can also be just an arbitrary surface. It doesn't have to be such a nice rectangular surface. And I'll pick some little patch here through which to look. Here is my, I don't want my normal vector to be going like this. I'm going to choose my normal vector to be like this. And my electric field, of course, will be like this, such that they make an angle. We'll call it theta. Yes?
Yes.
So in general, this delta phi, or delta phi, whichever you prefer, is going to be equal to E, the vector E, dotted with this normal vector to the surface, right? You know what I mean by a normal vector to a surface? We've talked about this many times, but in general, if I have a surface, the normal vector to it is always perpendicular to the surface, so however I turn it, right, this pen is the normal vector. It's pointing in a direction that's perpendicular to a tangent line to the surface, you see?
Yes.
Right, that's the normal vector. Times a delta A. So whatever this is. So if this is delta A, little piece of area. So I get a little piece of flux in this little piece of area, right? And I'm kind of allowing for this orientation of the surface using this dot product. But this, of course, a dot product, if you remember what that is. So just go over A dot B. If I have a vector A, right, and I have a vector B, A dot B is like the projection of A onto B, all right? And if I define it by the angle between them like this, then it's just equal to A, B, the magnitude of AB times the cosine of theta, okay? So I can write this as the magnitude of E, which I'm just going to write as just the E without the little vector bar over it, times the cosine of theta times delta A, right? So the flux is kind of a measure of the number of field lines passing through a surface, okay? So if I had a bright light and a dim light, which one would have a higher flux through the same surface? So if I held up, this is my reflector, right? And I held this up, maybe perpendicular, or such that the normal vector is aligned with the incident rays from the light, right? Would a bright light or a dim light have a higher flux?
Bright light.
Bright light, yes. There's more stuff, right? So if you're thinking of it as air, like air currents, right? A strong wind, where there's a lot of air rushing past, right, would have a higher flux than a light wind, okay?
Okay.
Or if it's a water hose, right? A lot of water, a big water hose, a lot of water flowing through versus a little bit of water flowing through, flux, okay? So this is just for an arbitrary surface, right? Now I want to think about closed surfaces. And what I really want to do is I want to put a closed surface around a charge, okay? So if I have a charge, say a positive charge here, positive Q, right? We know what its field does, right? We've seen this many times so far, right? Its field is always radially outwards like this. You can see that as you get farther away, the density of lines is decreasing, right? Now, of course, imagine this in 3 dimensions, so it's doing this in all directions, right? And so I put, it doesn't necessarily have to be a sphere, but that would be convenient, right? If I put a sphere around this, it's a closed surface. There we go. So here's my little closed surface. And I want to think about what is happening here. If I look at the net flux, right? Is it positive, negative, or 0? So think about the stuff flowing out of the surface, right? Maybe it would be easier to compare it with this. So we'll call this surface 1, right? S1. I'm going to put another surface over here. We'll call this surface 2. Now surface 2, you can see these field lines, right? Well, that seems to be the only field line that's going to hit it, right? The others are missing the surface. The field lines going in, right, are equal to the field lines going out, right? Because remember, we're going to have a normal at this point. Yeah? And we'll have a normal at this point. Yes?
Yeah.
Notice they're oppositely directed, right? So this is the negative of that, or that's the negative of this, however you want to look at it. So the stuff coming in and the stuff coming out, right, they're about the same. It's not exactly because the field will be stronger here and weaker there, but if we ignore that for a moment, right, we can see that the amount of stuff coming in is about equal to the amount of stuff coming out, yes?
Yes.
Whereas if I put the charge source inside the surface, then we are getting more out than is coming in, yes?
Yes.
Because in fact, as I've drawn it here, there's nothing coming in, right?
Yes.
Does that make sense?
Yes.
So there's a law, it's called Gauss's law, right? And it says that, where should I put it? I'll put it over here. Gauss's law says that phi net, this is the electric flux, okay, electric flux to be specific, is equal to 4 pi k, that's the Coulomb constant, times, I'll write Q inside. Okay? So the amount of flux that you get is proportional to or equal to 4 pi k, where k is Coulomb's constant, times the charge inside. So if there's zero charge inside, what's the net flux? See? Zero charge inside, the net flux is 0. Okay?
Okay.
Plus q charge inside, here we have a net flux, which is non-zero. It's greater than 0, right?
Yes.
Yes?
Yes.
I could, I suppose, if I wasn't talking about electric flux, I could have a sink, for example, right? If this was water, right? We had water flowing out and water flowing in, and we put a surface around the sink, right? So it's all flowing into the sink and then disappearing down the drain, right? That would be like a negative flux, okay? So does this idea of flux, do you get it? Can you see it in your mind?
Somewhat.
Somewhat? Okay. So looking at this charge picture, right? The sphere that we've drawn around it, right, is usually called a Gaussian surface, right? So the trick behind using Gauss's law to solve problems in electrostatics is picking the right Gaussian surface. You want to find something with a high degree of symmetry, right? A sphere centered. Okay, sorry about that. I had some technical issues. Had to lose the mic for technical reasons. Try to fix that later. So I'll try to speak up. Where was I? Closed surfaces, right?
Yes.
Yeah, so we always want to choose a Gaussian surface which is symmetrical to the charge distribution that we're considering, okay? So the key features here, notice that the electric field is always normal to the sphere surface, right? So that's important. It's the same angle throughout, okay? So you pick a situation that matches the symmetry of the problem that you're considering. So you would not use, for example, a Gaussian, you wouldn't use a sphere as your surface that you're going to calculate the flux through if you were looking at, say, a line of charge, right? Or an infinite line of charge, or a sheet of charge, all right? You have to pick it to match the symmetry of the problem. And if you can, then it makes it very, very easy. So in this case here, right, we would get that the electric field, right, is just equal to K. We have a plus Q charge inside, so let's put Q over, and let's choose the radius of this sphere to just be R over R squared, and that's in the R direction, yes?
Yes.
So note that if we want to calculate what the flux is, right, E dot in this case, is going to be, it's normal, right? So we would get, and then of course times delta A. This is going to be K, Q over R squared, R hat dot in hat. I know they look very similar, but sorry about that. And R dot in, since they are aligned, right, this is the same thing as having an angle of 0, which means that the value evaluates to 1, right? So that's giving me K, Q over R squared times delta A is equal to delta phi. So now the question is, well, what is this area, right? Well, it's the area of, it's the surface area of a sphere, okay? And does anyone happen to know what the formula for the surface area of a sphere of radius R is? No? Actually, I'm going to put a video up that shows how to derive this equation, but it's pretty straightforward. So I'm just going to write this as sphere, okay? And the surface area of a sphere is 4 pi R squared, okay? So if I substitute that in here, I get K, Q over R squared times 4 pi R squared. These two cancel. What am I left with? I'm left with 4 pi K times Q. And so you can see in this simple example, we've calculated essentially what Gauss's law tells us, okay? So we kind of confirmed it for this case. In the case of a single point charge that we enclose in a Gaussian sphere. We don't, keep in mind, this sphere is not real. This is just an abstract tool that we calculate with, all right? So we imagine putting this sphere around it. Doesn't mean you actually have to put a sphere around any charges, okay? Does that make sense? It's just a tool by which to calculate this, all right? But so you can see that that gives us the answer we were looking for. And so we see that the flux through this sphere is equal to 4 pi K times the charge inside, which is what Gauss's law tells us, okay? Let me show you something. Okay, so I've drawn a cube here, all right? And I'm going to label face 1 will be this face back here. That looks like it's on the front, doesn't it? Let's do it like this, maybe. Right? So that's face 1. Opposite that will be face 2. I'm going to put face 3 down here. Face 4, go up here. Face 5 is back behind here, yes? And face 6 will be this front face that we're looking at here, right? You see all these faces? So face 1 and 2 are crossing each other. Face 3 and 4 are the top and bottom, and then face 5 and 6 are the back and the front, right? I want to consider an electric field vector. Let's consider that it enters at some point here. This is my normal. And we'll let it just have some arbitrary, something like that. Yes? Then we'll consider a point directly across from this. The normal this time would be like so. And at this point, the electric field going through here would look something like this. Okay? So we'll call this E at 1, and we'll call this E at 2. Well, really, this is the x-axis, this is the y-axis, and then coming out is the z-axis, as I've drawn here in the compass rose, if you want to call it that. And this is really, when we take the dot product, when we project E onto this normal vector for face 2, right, this is really E sub x. I'm going to put comma 2 to mean at face 2, okay? So that's the x component of the electric field, right, at face 2. Similarly, back here, this is at face 1, but it's also the x component, so E sub x, comma 1, right? So if we consider the origin to be at x, y, z, right, some arbitrary point x, y, z, then this point right here will be the point x plus delta x, comma y, comma z, okay? It gets messy when you start going into 3 dimensions, and I apologize for that, but what can you do? Similarly, this point over here, right, if I draw an arrow to that, that's going to be the point x, comma y, comma z plus delta z. And this point way up here is going to be the point x, comma y plus delta y, comma z. Okay? Does that make sense? So in other words, this cube that I've drawn, right, has a face, the length of this face is delta x. This one into the page here would be delta z. And this one here, going up, is delta y. All right? Now, again, let's write that the flux out of face 1, right? Because look at the normal vector. It's pointed in the opposite direction as this normal vector is, right? So by saying phi sub 1, that's going to be minus because it's in the minus direction, right? E sub x through face 1 times dA, some little area element, right? We'll worry about dA in a minute. And phi 2, the flux out of face 2, is positive E sub x, comma 2 times dA, all right? It's not quite the same amount because, again, it's displaced by delta x, but as a first order approximation, right, what we can write is we can write that this is equal to the value at face 1, so we'll write E sub x, comma 1, plus, and these are a little bit like the derivative signs, the d, the dx, and things like that, except it's written with the Greek delta, okay? So delta E sub x over delta x. So what is that exactly? That's the change in E sub x for a little change in the x direction, okay? With, and the fact that we used the Greek deltas, right, is saying that we're holding everything in y and everything in z fixed. So there's no functional dependence on y and z. And then we're going to multiply that times a normal dx, right? So it's just a little bit of notation, but don't sweat it too much. And then this, of course, is going to be all multiplied times dA. But what is dA, right? dA is just going to be, you know, the delta x, oh, I'm sorry, not delta x. And actually, I don't want to use dx. I want to use delta x here, okay? We just write it as delta x. So what is an area element on surface 1? Well, it's got a little, if I drew the little element here, right? You can see that this part here, right, is a delta y, and this part here in this direction is a delta z. You see? So delta y, delta z. Does that make sense? It's a little complicated because we got to keep track of all of these different directions and stuff, but that's kind of a pain. But this little area element is delta x, or excuse me, delta y, delta z, right? That's the size of it. And I'm saying that the electric field at this point is the same as the electric field at this point, plus this little bit. And this is just how much it's changed over that little distance, dx, right? It's a variable dx. Dx, yes? Times that much. So it's like the rate of change of the electric field over distance times how far away it is, how much distance you've gone, you see? So if this electric field had a grade of, like this, right? You multiply it times how far did you go, it's just this little bit, so it puts you at this point here, you see? Make sense?
Yeah.
Okay, so that's the flux through phase 1, that's the flux through phase 2. Now I want to get the net flux through both phases. But I want to pair them up, right? Because it doesn't make sense to pair this phase up with this phase. Right? We really want to pair phase 1 with phase 2, phase 3 with phase 4, and phase 5 with phase 6. Okay? So we'll call it the net flux 1, 2, which is just the sum of these fluxes, right? T1 plus T2. And what's that look like? Well, we're going to add E sub x, 1 plus dE dx delta x minus Ex, 1 all times delta y delta z. So you see that this term, E sub x1, is going to cancel this term, E sub x1, yes?
Yes.
So what are we left with? We're left with just this part, right? Let me just rewrite it here. dE dx, this is dE sub x, by the way, times delta x times delta y times delta z, right? So we got the delta x because it was tied to this little, this rate of increase as we went from phase 1 to phase 2, right? And then we got the delta y and the delta z because that was the area, right, that we used when calculating the flux. We can do the same thing for phase 3 and phase 4, right? And it wouldn't surprise you, right, which is going to be phi 3 plus phi 4. It's going to look very similar, except it will be dE sub, for phase 3, right, we'll have x and z, so this is dE sub y, dy, times delta y, times delta x, times delta z, right? And then phi 5, 6, that's the combination of the flux through 5 plus the flux through phase 6, will be dE in the z component of the electric field, dz times delta z times delta x times delta y. But notice that we've got all three of these here, right? This is delta x, delta y, delta z. They commute, so this is really just a delta A, a delta V, right? That's the change in volume, right? Why volume? Because we have three spatial variables, right? That's a little delta V. And the total net flux is then equal to, well, one way to write it for a closed surface, as we've done here, right, is to write an integral, which is that, continuous sum, and put a circle around the integral sign. That means a closed surface, okay?
Okay.
And of course we have the E dot n dA. But as we've calculated from this, right, it's also equal to an integral of this plus this plus this, right, which gives us this term, dE sub x dx plus dE sub y dy plus dE sub z dz. And not delta V anymore, but I'll let this become dV now, right? It's going to be continuous variable. It's going to be dV and not delta V, yes?
Yeah.
This is an interesting thing because it looks a little bit like what we get from a dot product, right? Because if I take a dot product of something component-wise, right, I'll get a sum over the x, y, and z components, right? So as it turns out, this is the dot product of something. So the kind of the three-dimensional version of a derivative, right? So if I say, df dx, right? That's a derivative in one dimension, let's say, where f is just a function of x. Yes?
Yes.
Well, if it's a three-dimensional function, right? Something x, y, and z. Imagine like a hill, right?
Yeah.
If I stand in a particular place and I walk in a particular direction, I may have a rising slope, may have a descending slope. It'll be different than going from left to right, right? Of course, you've got the up and down component as well, right? So the kind of the version of a three-dimensional derivative is called the gradient, and it is a vector. Okay, so if I take and we write it with an upside-down triangle, I know, more weird notation, right? So right, and so this is actually a vector that has components, right? It's a real pain. df sub x dx. That's the x component. All right, it's df sub y, dy, dy, df sub z, dz. Okay? It's a vector, right?
Yeah.
And if I think of this as an operator, much like we do with the derivative, we think of the derivative as an operator, something that we can operate on a function with, right? This is an operator too. And an interesting thing that you can do is you can dot it with another vector quantity. Usually they don't write a vector hat on the del operator, but it's a vector. You can operate this on a vector. Let's call it E. Yes, that's a good idea. On a vector E, and what it ends up being is it looks like a dot product, right? Where you just simply sum the components, right? It's the product of each of the components one at a time, right? So A dot B is A sub x times B sub x plus A sub y times B sub y plus A sub z times B sub z, right? And that's what you get here. Del dot E would be equal to partial of E, the x component of E with respect to x, plus the partial of E, y component of E with respect to y, plus the partial the z component of E with respect to z, add it up. And that looks exactly like this, doesn't it? So this is actually what this is, and so you get two ways to write this. Let's just do it like this. P net equals, this is called the divergence. So del dot E, we call it the divergence of E, okay? And this is either Gauss's theorem or Gauss's law. Did I get that? No, this is Gauss's law, okay? So we can write Gauss's law in terms of this, right? So let me just make some room up here. We can write, yeah. So this is one way to write Gauss's law. Or we can write this, where this is the charge density, okay? The equivalence, so here we wrote in terms of the total charge inside. Here I've written in terms of the charge density. And the reason why is because if we integrate both sides of this, right? So if I were to integrate del dot E dV, this would then be equal to the integral of this, okay? Rho dV. Well, being constant, right? The charge density is just a number, and so this just gives me the total charge. You see, and so we end up with 4 pi k times q inside, right? But for whatever reason, people like to write it like this without the integral, and so you write it in terms of the charge density instead of the total charge inside, right? So this tells me that if I put an enclosed surface around something that has a charge density, then there's going to be a divergence. A divergence means that the net flux will be a positive quantity, okay? And so that's the way to kind of think about this. Yeah, so this is Gauss's law, okay? You can use either form, and it's also, more importantly, right, either of these is an expression of the first of Maxwell's equations. Maxwell's equations will be very important for us later on. We're going to try to get all 4 of them. So far, we just got 1. Maxwell's equations are enough to tell you everything you need to know about an electrical system, okay? Covers everything that can be said about electromagnetism. It's really this is kind of Maxwell's equations form of Coulomb's law. Think about it. Okay. A couple of things. K. Sometimes people like to write things a little bit differently, so I'm just going to make a little more space here. Also, you can write the right-hand side of this could be written as Q inside over, I think it's 2 epsilon naught. Is that right? K, right, is equal to 1 over 4 pi epsilon naught. So K, I guess it's just epsilon naught. There we go. Whereas this one would also just be rho over epsilon naught. K equals 1 over 4 pi epsilon naught. So this is just another fundamental constant. It's called the permittivity of free space. Permittivity, think of the word permit, right? So it's like a selectivity. You can think of it as the opposition to the electric field from free space, okay? It'll make more sense when we start talking about materials, which are going to create an opposition to the electric field. So that's why it's called the permittivity of free space. By free space, we're talking about space without matter present, okay? So like in a vacuum. For all intents and purposes, though, like in air is kind of considered free space too, because air doesn't offer much resistance to electric fields. But we'll talk more about that later. Just an alternative form of it. You can either write it with the Coulomb's constant or with the permittivity of free space. This is the conversion factor. Okay. So I promised that this would make life really easy, right? It seemed kind of complicated and weird, right? But this somehow is a benefit to us. So let's see what that benefit is. I don't remember, what did I work in class last time? Was it the infinite line charge or the infinite sheet of charge?
It was line charge.
I think it was. I'm pretty sure I put line charge on your homework. So you have to do that using Gauss's law. So I'll do a sheet of charge, okay? Which I only just told you what the answer was last time. We didn't calculate it. If I did the line charge example, then I wouldn't have calculated the sheet of charge. So, but you remember it was quite a bit of work to calculate the electric field due to the line charge, right?
Yes.
Yeah. A lot of equations and algebra and trigonometric substitutions and stuff. So here is an infinite sheet of charge. Obviously, I'm not drawing infinitely large, right? So we'll just put plus charges pretty much everywhere, right? And I want to consider, so what's my Gaussian surface, right? The shape doesn't really matter so much. So I may as well use a little box shaped like this. Yeah. Oh. So, but it goes through to the other side. See? So again, these Gaussian surfaces can pass through solid object. That's fine, because it's just an abstract idea that we're doing, right? It's not real. So just so we illustrate this little box that I've drawn, right? The top of it is up here, and the bottom of it passes through this surface and comes out the other side. Okay. The sides of the box are perpendicular to the surface of this infinite sheet of charge, okay? So we're going to calculate the flux to it. So the only place the flux is going through the top and the bottom surface of our little Gaussian box we put here, right? It's not passing through the sides at all because the sides are parallel to the direction of the electric field. Remember, when we lay charges down on a surface, allow them to distribute themselves uniformly, they will have a field which is normal to that surface, okay? Just like the walls of my little Gaussian box that I put on here, you see? Can you see the box? I'm not the best three-dimensional drawer. I'm looking for something that looks box-like. Here. This eraser looks box-like. So this might be the top of it, right? And if I could see below it at the same time, I'd see the bottom of it coming out like this.
Yeah.
Right? The walls of this box are perpendicular to the surface, right? Just like the electric field coming out of this surface, okay?
Okay.
So, what do I do to calculate the electric field? Well, if we just think of the electric field coming out, right, E dotted within is just going to be the magnitude of E, right?
Yes.
This is going to be my little delta A, right, my little area. But I also have flux coming in from the bottom, right? So I'm just going to say that the net flux is going to be 2 times E. So the E dot in, right? Maybe I should write this out in detail for you. We're going to integrate over this surface, right? We're going to 2 times it because we're going to treat the bottom as well as the top. E dot in, right? That's just E, the magnitude of the electric field, dA. This is going to be 2 times E times this integral, the surface area integral, dA. There's nothing in here, so that's just A. You see that? So this is equal to 2 times E times A. The charge density, right? How much charge? Is given by sigma. Remember we said for surface areas we use sigma, for volumes we would use rho, and for lines of charge we use lambda. So the amount of charge is given by sigma, so if I were to Q is equal to sigma times A, right? I multiply the area times the charge density, then I get the amount of charge, right?
Yes.
Gauss's law says, now that I've written out what the flux is, right, it's 2 times EA, right? That is equal to 4 pi K times Q inside, but Q inside is just the charge density, sigma, times A. See that?
Yeah.
But look, this A and that A are the same A, right? Those cancel. And so I'm left with 2E equals 4 pi K times sigma. Let's divide out the 2. So we now have solved for E. Dividing out 2 gives me 2 pi K sigma. Alternatively, right, using this relationship here, since K is 1 over 4 pi epsilon naught, that means that this is equal to sigma over epsilon naught. Pi cancels, and we're still left with a 2. There we go. Yeah. Might be off by a factor of 2, but that's okay. So there it is. There's the electric field. Right? It's a constant. It's proportional to the charge density. And that's it. Right? There's no dependence on how far away you are from it. Seems kind of weird, but remember, it's an infinite electric field. It's a plane, an infinite plane of charge, right? And so the electric field is constant as far away as you want to get from it. Okay?
Okay.
Does that seem easy enough?
Yes.
Yeah? It's all about choosing the right Gaussian surface. Okay? I think that's all I have for you. Yeah, I have a homework assignment, of course, but is there any questions?